All right, class, welcome back to college algebra. We have 5 lectures to go this semester. So let's look at our last exam. Find the vertical asymptotes and state the domain for the following functions. So vertical asymptotes, remember, that's where you get 0 on the bottom. All right, so if 3x minus 10 is 0, then 3x is 10, or x is equal to 10/3. So that's where the vertical asymptote is. As far as the domain is any number you can plug into this function where you get a number back. And the only number you can't plug in is 10/3. So you could simply say x cannot be 10/3. Or you could say all real numbers except for 10/3. Or you could say negative infinity to 10/3 union 10/3 to positive infinity. Okay. Number 2, same kind of thing here. What you might want to do is just factor the bottom. This is the difference of 2 squares. So you could easily say this is x minus 4 times x plus 4. So you get your negative 16, your x squared, and then your minus 4x and positive 4x cancel out. So by looking at it, you could say, okay, the asymptotes are at x equals positive negative 4. All right. Asymptotes at x equals positive negative 4. Oh, this one. Okay. And the domain is everything except for positive negative 4. Because if you plug those in, you get 0 on the bottom and this thing is undefined. Or you can write that as all real numbers except for positive negative 4. Or you could say negative infinity to negative 4, union negative 4 to positive 4, and then 4 to infinity. Okay. I guess I could give number 1 a little more room here. Yeah, that's a little better. And here I'll say isum at there. There we go. So there's your exam number 23. They're not asking you to solve for x. They're not asking you to graph. They're only asking you where the vertical asymptote is and state the domain. So there's not a whole lot of work in this problem. So let's get our quiz on. This is quiz number 24. So let's see, let's do this one here on page 164. So here's the first part of it. A, B, and C. And then number 2, let's say, well, let's do this one. All right, these should not be very difficult. Again, we're looking at asymptotes. So we'll take 10 minutes to do this one. So 10:45, I'll work them for you. In the meantime, I'll put you on the breakout rooms out there. Okay, let's see here. Let's make some room. Move number 2 down here. So if D equals RT, where D is distance, R is rate, and T is time, solve for T. Okay, well, if D is RT, we could write this as RT equals D, of course. All we're doing is switching both sides. Divide both sides by R. So T is D over R. The distance divided by your speed gives you your time. All right, that one's easy. Now let's look at B. How long will it take to drive 195 miles? So that's your distance. If your speed is 60 miles an hour, they say average speed. Well, if your rate is, if you're going at a constant speed, then your average speed is your constant speed, right? If your speed never changes, then your average speed is just going to be your constant speed. So we already have T equals D over R. Well, they said D is 195 and R is 60. 195 miles over 65 miles per hour. So look at your units here. The miles cancel out. You have 1 over hours. All right, so always look at your units. Your units are what guide you. So we take 195 divide by 60. We get 3.25. And it's 1 over hours, which gives you hours. Anytime you're trying to manipulate equations that are in the physical world, look at your units. You know, if you take physics 1 and you have all these different kinds of units and you don't know how to manipulate your equations or which equations to use because there's so many different formulas, look at the units. You know, if they're asking you for units of charge, look at the formula that gives you units of charge instead of, you know, atoms or, you know, dollars, you know. All right, so now part C. What happens to time if your speed approaches 0 miles an hour? So what happens to time? Well, we have time is D over R. R is your rate. So if the speed approaches 0 miles an hour, well, if the bottom of this goes to 0, what happens if you divide by something really, really, really small? You end up with something really, really big. Okay. If you divide by something small, you end up with something really big. So the time goes to infinity. Obviously, if you're driving 0 miles an hour, it's going to take you forever to get anywhere. Real simple question, right? If you forget that you're in a math class and they ask you this question, you'd know the answer right away. When you sit in a math class, you're like, oh, this is math. I don't know. All right. You got to use your common sense. The way we'd write this in mathematical jargon, we'd say the limit as R goes to 0 of T is the same thing. Limit as R goes to 0 of D over R, because T is D over R, equals infinity. Because as this goes to 0, this whole thing goes to infinity. That's how they would write that in calculus class. Okay. So number 2, suppose it costs C dollars in billions to build X miles of a wall along the US-Mexico border, given by this function C of X. To approximate to the nearest million, how much would it cost to build 1,000 miles of such a wall? So we have billions and millions. So we want to make sure that we, adhere to the requests here. So, so we want to build 1,000 miles of wall. Well, X is miles of wall. So all we have to do is plug in 1,000 into our formula. 0.425 times 1,000 over 1954 minus 1,000. So let's see, if we multiply the top by 1,000, we get 425. 1954 minus 1,000 would be 954. So if we plug this in our calculator, 425 divided by 954, we get 0.4454926, etc. All right, but they say this is in billions, right? So we'd say, okay, we'd have to multiply this times a billion, right? So what's a billion? Let's see, that's 1,000, that's a million, that's a billion. So we get 9 zeros, right? I'm going to put this in parentheses. 9 zeros. So we move the decimal to the right 9 times. So let's see here. I wonder if I have enough decimals here. 1, 2, 3, 4, 5, 6, 7, 8. No, I need another decimal. Hold on. 2, 6, 6, 2. And there's more decimals. It keeps going, right? So we need dollars here, right? Because this is the cost in dollars. But they want us to round this to the nearest million. So let me put some commas in here. So let's see, this would be the millions place, right? So we're looking at, since that's a 4, we leave this 5 alone. So this would be $445 million or 0.00000, $445 million. So again, all we did was plug in 1,000 into the function and then round. All right. According to this model, how many miles of wall would be impossible to build? Well, you can't get 0 on the bottom, right? So you can't have 1,954 miles because you can't divide by 0. Right? What does this mean physically? I'm guessing the whole border is 1,945 miles. It means that no matter how much money you spend and no matter how hard you try, there's still going to be a tiny hole somewhere. It's just impossible to make a wall that long in that location that doesn't have at least a small hole somewhere. Okay. So let's see, where did we leave off last time? We are now prepping for exponential functions on page 167. And we're going back to percentages because we're going to use exponential functions to deal with interest rates. It's one reason. So convert the percents to decimals. So remember, percent means per 100, right? Per cent. That is century or 100. So when they say 65%, they mean 65 per century or 0.65. So when you convert a percent to a decimal, you're simply moving the decimal to the left twice. So this one would be 10.5 per 100. So this would be 0.105. 0.25%. This is 0.25 per 100. So this would be 0.0025. All right. Students often get these right. Oh, I moved the decimal to the left twice, but when there's a decimal here, students have a tendency to just put 0.25. That's wrong. You still have to move the decimal to the left twice. So it's 0.0025 because it's a quarter of a percent. So 8 3/4%. This is 8.75. That's what 8 3/4 is per 100. So this would be 0.0875. 0.0045%. This is 0.0045 per century. So that would be 0.000045. 7 3/5%. If we take our 3/5, 3 divided by 5, that's 0.6. So this is 7.6 per cent or 0.076. So here we have a negative percentage. This is negative 0.035% or negative 0.00035. Just moving the decimal to the left twice every single time because you're dividing by 100. That's what percent means, per 100. All right, so number 8 here. Some more simple stuff. Match the expression to the correct definition. Let's start with the letters. 3 multiplied by itself X number of times. 3 times 3 times 3 times 3 X times. All right, that's 3 to the X. That's what the exponent means. You're multiplying the number 3 times itself X times. A number divided by 3. A number divided by 3, also known as 1/3 X. 3 less than a number. So you have a number and you take 3 away from that, you have 3 less than a number. So let's see. A number multiplied by itself 3 times. Here's a number, multiply it by itself 3 times. This is X cubed. So this is D is up here. 3 more than a number. Take a number, add 3. Now you have 3 more than a number. So that's E. A number multiplied by 3. Here's our number, multiply it by 3. So that's 3X. All right, discuss whether 10 to the X is the same as X to the 10th. No, they're definitely not. 10 to the X is 10 times 10 times 10 times 10 X times. But X to the 10th is X times X times X times X 10 times, right? Let X equal 2. And let's look at an example. 10 to the second power is just 10 times 10 or 100. 2 to the 10th power is 2 times 2 times 2 times 2, 10 times. So what would that be? That would be 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128, times 2 is 256, times 2 is 512, times 2 is 1024. This is 1024. 2 to the 10th is 1024. If you deal with computers at all, you might recognize those numbers. Because in computer science, you only have zeros and ones. Instead of base 10, you have base 2. So the powers of 2 show up all the time. That's why your hard drives are like, you know, this many megabytes is a gigabyte. All powers of 2. All right, page 168. Answer the following. Steve wants to invest $500 this month in an account that earns 1.07% interest. If he leaves his money in the account, how much will he have in 5 years? So we need some vocabulary here. Let's look at simple interest. So let's say P is the principal. Okay, we'll use R for the annual interest rate. Annual, that means every year. Okay, so if it's 10% annual interest rate, that means at the end of 1 year, there's 10% added to the principal. Okay, T is the time in years, because the rate is annual. That's how you know the time has to be in years, because the interest rate is an annual interest rate. It's all based on years, okay? Otherwise the formulas don't work. And then the A is the amount after T years. So simple interest, we'll call this I, interest. Okay, so simple interest is going to be, if you take your interest is going to be your principal times your rate times your time in years. Makes sense, right? You take $1,000, let's say $100, and let's say your rate is 10% and it's 1 year. You just have 100 times 0.1, which would be $10. All right, so I par T, you can remember that. I party, that's your simple interest formula. So your amount is your principal plus your interest, right? Well, if your interest is PRT, you can factor a P out. You got P times 1 plus RT, okay? So here's your two formulas. Simple interest, there's just the interest. And again, your amount is principal plus the interest, all right? Then we have, now what if instead of compounding your interest at the end of every year, a lot of times what they do is they'll compound it monthly. So what does that mean? That means, let's say if you had 12% interest rate, instead of waiting at the end of the year and taking 12% of your principal, what they're going to do is each month they're going to charge you 1%. And what happens though is that the second month, you're not only getting interest on your principal, you also are getting charged interest on the interest that accrued in that first month. So if they compound the interest more often than once a year, you pay more. You see, because come the third month, you're not just paying interest on your principal, you're also paying interest on the interest earned on the first month and the interest on the second month, but also on the interest from the first month. So the more often that you compound interest, the more interest you pay, because the more you're paying interest on the interest on the interest on the interest. It's called compound interest. So compound interest, try that again. Compound interest. So we have all the same formula, the same letters as before, but N is number of times compounded in a year. So again, the more often you compound it, the more times you're paying interest. So here the amount is P times 1 plus R to the NT. So it looks kind of like this one. Notice the simple interest, it's just P times 1 plus RT. Well, here we have this exponential where N is the number of times you compound. So if it's monthly, N would be 12. If it's daily, N would be 365. Okay, so what this exponential does is it takes into account that you're getting charged interest on the interest on the interest, right? Simple interest is the least amount you're going to pay. Simple interest doesn't even compound it at the end of the year. Let's say it's 10 years. They don't compound the interest at the end of 1 year. So the second year, you're not paying interest on the interest from the first year. No, simple interest, if it's a 10-year note, they just wait till the end of the 10 years and they just calculate the interest once. Okay. So if you're compounding interest annually at the 10 years after the first year, during the second year, you're paying interest on the interest from the first year. Okay. So that's if they compounded it annually, that would be N equals 1 time per year. Okay. Notice if you put a 1 here, this does not simplify to this. All right. The T is still in the exponent. Okay. So simple interest is the cheapest, right? Nobody uses simple interest. They all use compounded interest. Okay. Now, if the more times you compound, the more interest you pay, what if they compounded like every second? Just so that on that second you pay interest on the first second, and on the third second you pay interest on the interest of the first and the second. I mean, by the end of like, an hour, you're paying interest on the interest 60 times over. Well, it's more than that. That would be at the end of the first minute, you'd be paying interest on interest 60 times over, right? So what if they compounded every millisecond? The best you can do is compound continuously. And it turns out that as N goes to infinity, you end up with E to the R. Hold on. Let me make sure I write this down right. The RNT. Continuous compounding interest formula. Yeah, we need P to the RT. There we go. We still have the P. It turns out that this thing, as N goes to infinity, this thing here turns to E to the RT, where E is Euler's number, which is 2.7 something, something, something. It's one of the physical constants of nature. It's like pi, but it's E. It's our natural base. So on your calculator, you'll see a log button, a log base E and such, which we'll get to that. It's the opposite of the exponential. Okay, but you'll see an E to the X button on your calculator. All right. So E is a number. It's like pi. It's a transcendental number. So that's what happens if you compound continuously. It does limit out. It doesn't end up having an infinite amount of interest, even though you're calculating interest on interest an infinite number of times. All right, so you'll have 3 different formulas: simple interest, compound interest, and continuous compound interest. So this one is continuous compound interest. Okay. Compounding or continuously compounding. So here they haven't even introduced any of this stuff yet, right? So Steve wants to invest $500 this month. So that's the principal, and an account that earns 1.07% interest. So the rate R is going to be 0.0107. You have to convert the interest to a decimal, because if you stick a percent in here, it's not going to make any sense. The formulas don't understand the percent symbol. They understand numbers. Okay. Again, what this means, percent means 1.07. Percent means per century, which is 0.0107. That's the number the formulas want, because this is this. All right, the formula doesn't understand, it can't compute percent symbol. That's just something for us. All right, he leaves his money in the account. How much will he have in 5 years? Okay. They didn't tell us, is this, how often they compound the interest. They didn't say compounded annually. They didn't say anything about how often they're compounding. So we assume simple interest. Okay. What is the interest rate? Right there as a decimal. There it is as a percent. Here it is as a decimal. How much does he want to invest? 500 bucks. How long is he leaving his money in there? 5 years. So this problem, all I wanted you to be able to do is identify the parts. Okay. In this class, we slowly lead into things. Steve wants to invest $500 this month. So that's our principal. And here's our interest. R as a percent is 0.0107. He leaves his money in the account. How much do you really have in 5 years? So T is 5. Oh, but now this thing is compounded weekly. So if it's compounded weekly, N is 52. Okay. So this last example, we would use A equals P times 1 plus RT, right? Simple interest, right? Let's write it out again. Remember, I party, right? I party. The amount is principal plus interest, all right? And the interest is PRT. If you factor out the P, you get P times 1 plus RT. So we would use that formula for the simple interest because they didn't say anything about compounding. Here, they say we're compounding weekly. So we need to use our formula for compound interest. So we would use P is 500. R is 0.0107. N is 52. And the time is 5 years. So it's one thing to be able to write down the formula. What most of y'all are going to make mistakes doing is plugging this into your calculator. Right? Most students I've ever had can never plug these into the calculator and get the right answer. Let's simplify this thing. If we add 1 to 0.107, we get 1.0107. If we take 52 and multiply it by 5, 52. If you're using an iPhone or real simple calculator, you kind of have to break it down like this. We need to multiply this out. Okay. Now, you can't just type this in from left to right and expect to get the right answer. With a regular basic calculator, you kind of have to work your way from the inside out. So the way you would do this is you would start with this number, 1.0107. Okay. And now you have to hit the X to the Y. That means to the power of, and then type 260, hit equals. And now we have that into our calculator. That's 15.91. And then multiply by 500. And we get $7,957.18, which sounds reasonable, right? Does it? $500, 1% interest for 5 years. I don't know, $7,000 after 5 years at 1% interest. I think something's wrong here. 1 plus R to the NT. Yeah, 1.071. 52 times 5 years, 52 times 5. Yeah, let's try this again. 1.0107. 1.0107 to the 260. 500. Well, I'm getting 7,000. This sounds like a lot to me, though. Hold on. P 1 plus R to the NT. Oh, I'm missing something here. You can't just do the R here. It's R over N. You see, if you're doing it monthly, let's say your interest rate is 12%, okay? Well, if you're compounding monthly, you have to take your interest rate and divide it by 12. So you'd only do 1% each month instead of 12%, right? It's 12% for a year. Does that make sense? So the number of times you're compounding, you have to divide by that much. So I missed an N there in my little formula. So this, we need an N. Boom. So we don't charge 1.7% every day, right? Or every week. We'd have to divide that by 52. You take the interest rate and divide it by the number of times you're compounding that year. Again, so if you're doing it monthly, if you had 12% interest rate each month, you'd only charge them 1% interest. Does that make sense? So here it's weekly, so that we're compounding it 52 times a year. So we have to take our interest rate and divide it by 52. But we're doing it 52 times the number of years. So this is the number of times you're charging actual interest. So it's 5 years times the 52 times a year, but you're only doing the interest rate divided by 52 each week. So let's fix this. I knew that sounded like way too much. So we have 1 plus, if we take our 0.0107 and divide by 52, this is 0.0002057 and so on. To what was it? A 260 up here? 52 times 5. Yeah, 260. So we got $500. All right, we take 0.0107. Really, I do this one fatal swoop. See, we've already rounded here. All right, so instead of doing that, I'm going to plug this into my calculator all at once. I'm going to start with this 0.0107. Now I'm going to divide by 52, and I got some decimal. All right, now I'm going to add 1 plus 1. Now I got 1.0020577. I haven't rounded anything yet, right? Now I'm going to hit to the power of 260, right? So this is 260. So this is like 1.0002057. Again, that's what's in my calculator, all right? Now I hit to the power of 260, and I have 1.05 something something. So now I have this in my calculator. Now I hit times 500, and we're getting $527.48. Big difference, right? 7,000. You only got 1% interest, and you only started off with $500. You're not going to end up with $7,000 after 5 years. All we get is $30 after 5 years. And this is the kind of interest rates that we're getting right now. If you're investing money, that's about all you're going to get, maybe 2% at the best in your bank account. Of course, you know, inflation is over 7%. So no matter what you invest in, unless you're rich and you can get into something really good, no matter what you invest in, you're going to lose money. That's why poor people have a tendency to spend it as fast as they can, because it's losing its value every day. So you may as well spend it while you can. All right. And if you're rich, the government just gives you billions of dollars in subsidies for doing nothing. All right, Miranda is going to invest her money in an account that earns 1.25% interest. So here's our rate. As a decimal, that's 0.0125. Compounded monthly, so that means N is 12. If she leaves her money in the account for 16 months, all right, that's our time, but we have to convert that into years. You cannot plug 16 in, okay? You have to convert that to years. This is 16 months would be a year and 4 months, right? So that would be 1 plus 4 over 12, right? 4 out of 12 is what, a third? Is that right? Yeah. So this would be 1.3 with a bar over it, years. How much will she have at the end of 12 months? 12 months means 1 year, right? So what is the interest rate as a percentage? Well, the interest rate is 1.25%. As a decimal, it's 0.0125. How long is she leaving her money in the account? 12 months, which is 1 year. A year. Answer in months, then years. There you go. Oh, no, wait. That's, yeah. She's leaving it in there for 12 months. Wait a minute. If she leaves her money in the account for 16 months, how much will she have at the end of 12 months? What the hell? Okay, well, she's leaving her money in the account. She leaves her money in the 16 months. So 16 months, which is again 1 and a year and 4 months, which is 1.3 years. That's just a really weird sentence. Yeah, she leaves her money in the account for 16 months, but then they want to know how much she'll have at the end of 12 months. So how much will she have at the end of 12 months? We use our formula, P1 plus R over N to the NT. So our principal, oh, they didn't even tell us. It depends on what the principal is, right? But if we knew the principal, let's see, the interest rate is 0.0125. We have to divide this by 12 because it's compounded monthly. Then we have 12 times at the end of 12 months. So to answer this question, T would be 1. Okay. So if we were going to, we can at least simplify that. So we'll start here. 0.0125 divide by 12. Now add 1. Now do the power of the X to the Y button. 12. So this is, all of this is 1.01257 and so on. So they didn't give us a principal, but whatever the principal is, we'd multiply it by this number and that would give us our amount. Okay. They haven't actually introduced the interest formulas yet. They don't actually want us to calculate the interest yet. They just want us to break down the problem. Samantha is going to invest $100, 15 months. So T would be a year and 3 months, right? So this would be 1.25 years. 2.5 interest rate. This is 2.5%, which would be 0.025 as a decimal. How much money will she have if it's compounded weekly? Compounded weekly, that means N is 52. There's 52 weeks in a year. Interest rate as a percentage, 2.5%. As a decimal, 0.025. How long is she leaving her money in the account? 15 months. Again, which would be a year and 3 months. So that'd be 1.25 years. Okay. If we're going to set this up, how much money will she have if it is compounded weekly? Well, it depends on how long. How long is she investing it? All right. Oh, wait, 15 months. Okay, so 15 months, the amount, principal times 1 plus R over N to the NT We have $100. The interest rate is 0.025, but we're doing this 52 times a year. So we have to divide the rate by 52, and then we have 52 times 1.25 years. So the way I do this is, first I need to figure out what this number is. 52 times 1.25. I need to know that ahead of time. That's 65. So now that I know that's 65, I start from the inside, work my way out. 0.025 divide by 52, add 1. Now hit to the power of 65, and I have a 1.03 and so on. Now multiply by 100. And I get $103.17. So she made $3 in a year and a quarter at 200. Not very good, huh? So let's look at exponential functions here. And we'll come back to interest and stuff. The graph of the quadratic function x squared is shown. So you remember x squared, all right? Whatever the input is, you square it, and that's your output. Now, an exponential function is modeled by b to the x, where x is your variable and the base is a positive number. All right, so we're sticking with positive bases here, okay? So exponential functions is where the variable is in the exponent, okay? So here's an example. It's one of the most simplest exponential functions. If you have 1 to the x, 1 to any power is just 1. So that's not an exponential function. That would just look like this, right? 1, okay? So the next number up is 2. So 2 to the x is the most basic one. So if we look at negative numbers, well, let's see, what do they do here? Yeah. 2 to the negative 2. Remember, a negative exponent is like how many times you divide by that number. All right. So this would be a 1/4. So over here at negative 2, we're only at a 4th. 2 to the negative 1, that's 1/2, which is, 1/2 or 0.5. At 0, 2 to the 0, anything to the 0 power is 1. So that's why right there, every single exponential function is going to go through that point. Anything to the 0 power is 1. So all our exponential functions look like this. They do this, they could be like that, or they might be like that, or they might be like that, or that. They all look like that, okay? They all look like that. They all go through this point. Again, because anything to the 0 power is 1. So 0, 1, 0, 1, right, is always a point on an exponential function, unless they put something in front of it, So 1, 2 to the first power is 2. So over here at 1, we got 2. 2 to the second power is 4. So up here at 4. 2 to the third power is 8. So you can see why an exponential function, it blows up, right? Now you might think x squared, look kind of like this, right? Well, x squared doesn't blow up as fast as 2 to the x, right? I mean, compare these, like 1, 4, 9, 16. You're just squaring the next number. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So 4 squared is 16. Where are we at with 4? 16, right? So that's where they're even. The next step, 5, right? 2 to the 5th is 32, but here at 5, we're only at 25. Once you get 6, 6 squared is 36, but 2 to the 6th is 64. So you can see that right there at x equals 4, that's where x squared is equal to 2 to the x when x equals 4. After that, the 2 to the x gets bigger much faster. So that's why you talk about exponential growth. That's why we talk about COVID, all right, diseases, pandemics, they spread exponentially. Okay. If it's spread like an x squared, it wouldn't be such a problem. But when things grow exponentially, they get big really quick. So here's our interest formula, compound interest, which we've already discussed. A equals P times 1 plus R over N to the NT. So A is the final amount, P is the initial amount or principal, R is the rate expressed as a decimal, N is the total number of compounding times in a year, and T is time. All right, the number pi is a mathematical constant that appears throughout mathematics and physics. When rounded to 5 decimal places, pi is 3.14159. The number e is another mathematical constant, sometimes called the natural base or Euler's number. When rounded to 5 decimal places, it is 2.71828. The natural exponential function is given by e to the x. So we looked at 2 to the x. We can have 3 to the x, 4 to the x. You can have any number to the x power. But the natural exponential function is e to the x, because in nature, that's how things grow, e to the x. Okay, so look at it. It looks exactly like 2 to the x. But because e is bigger than 2, it grows faster. So 2 to the x would be kind of like this. It wouldn't grow as fast. Okay, you can barely tell the difference, you know, but e to the x grows faster than 2 to the x. But again, boom, right? E to the 0 is 1. So 0, 1 is a point on its graph. All right. So again, if you compound continuously, you end up with P e to the RT, right? And basically what happens is, right, you had A equals P 1 plus R over N to the NT, right? As N goes to infinity, right, this goes away, but you end up with 1 to infinity power. This whole thing, the P stays the same, but that goes to e to the RT. That's how you get continuous compounding of interest. I need to fix this up here. Yeah, all right, that's right. Okay, so compounding continuously, that's where n is infinity. And that's how you get that e in there. Okay, what is it? How do I do this? Yeah, 1 plus 1 over n to the nth power. I think that's it. This goes to e. I mean, e. It turns into e as n goes to infinity. All right. Now this has r's and t's. And that's why you end up with an r and a t here. All right, we could take a short break and we'll come back to this break. We'll take a 10-minute break. So resume at 11:43. All right, class, moving on. So let's graph some of these, y'all. There's 2 to the x. All right, we already looked at the graph of this. Remember, 2 to the 0 is 1. So 0, 1 is a point, right? 2 to the negative 1 would be 1/2. 2 to the negative 2 would be 1/4. 2 to the negative 3 would be 1/8. So as we go to the left, this thing gets smaller and smaller and smaller and smaller. It never becomes negative though, because 2 to the negative 10 would be 1 over 2 to the 10th, which is really, really small, but still positive, right? Now, if we go to the right, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is way up here, 16, and by the time you get 2 to the fifth, you're all the way up here at 32. Okay, so exponential functions get big real quick. The domain is numbers you can plug in where you get a number back. You can plug in any number you want here and you're going to get a number back. Okay, if you plug in a negative number, you get something really small. You plug in a positive number, you get something really big. So the domain is all real numbers. Okay, now the range is the output. Notice there's nothing down here. All right, this thing may get closer and closer to 0, but it never reaches it. So we have to put a square bracket there. All right, it's always greater than 0, but it goes up to positive infinity. The y-intercept, here's your y-axis, it intercepts at 0, 1. Okay. I remember to hit, yeah. Okay, good. So that's 2 to the x. Oh, here's 5 to the x. All right, it's going to look pretty much exactly the same, okay? 5 to the 0 is 1. So 0, 1, it goes to the exact same point. All right, 5 to the negative 1 would be 1/5. So back here, at negative 1, we're at 1/5. 5 to the negative 2 is 1 over 25. So at negative 2, we're already so tiny, we can't tell. So this thing goes to 0 real quick as you go backwards. All right, 5 to the first power is 5. 5 to the second power is we're already up here at 25. So this thing blows up real quick. So it looks just like the other one. It just gets bigger faster. Okay. Domain, this thing goes infinitely far to the right and to the left. So it's all real numbers. Range, it never hits 0, but it goes up forever. Y-intercept is 0, 1. So same answers. All real numbers, 0 to infinity, 0, 1. All exponential functions have the same domain, the same range, and the same y-intercept. Okay, well, your basic exponential functions. You can always add stuff to them, right? You can always have, see, we're talking about b to the x, right? You can always multiply them by an a and then add something to it. Just like we did with our polynomials, you had an x cubed or an x squared, you could always multiply something by it, add something by it, all right? All right, now this one's a little different. They throw a minus sign in there. So we saw that when x was just a positive, without the minus sign, these things look like this. What that minus does is now when you plug in negative numbers for x, they become positive. And if you plug in a positive number, they become negative. So you're making your x negative just flips this thing over. What used to be positives, when you plug a positive number in, it would go up. Now you have to plug a negative number because a negative negative is a positive. So when you plug in a negative, the 3 to the gets a positive. So all it'll do is flip it. Okay. So let's look at this. 3 to the negative 0 is still 3 to the 0, which is 1. So it still goes through this same point. If I plug in a negative 1, I'm getting a 3 to the first power, which is 3. So at negative 1, I go up to 3. If I plug in a negative 2, I'm getting a 3 squared, which is 9. So at negative 2, I'm up here at 9. So this thing goes that way. Now, if I plug in positive numbers, if I plug in a positive 1, I'm getting a 1/3. 3 to the negative 1 is 1 over 3. So if I go to the right 1, I'm at 1/3. If I go to the right 2, I'm getting a 1/9. Okay, so if you make this negative, this is what you call exponential decay. So if you're looking over here, this thing is decaying exponentially. It's getting smaller and smaller. Whereas up here, we're looking at exponential growth. All right, so you'll see these two different kinds of functions a lot because these things happen in nature all the time. Things grow exponentially like populations, or things decay exponentially like half-lives of radioactive stuff. It's like how much time it takes for it to lose half of its quantity. That would be an exponential decay. And we'll look at plenty of examples of these here. So let's review. Simple interest formula, I par T. So the amount is principal plus interest. Interest is party. Factor out a P, you get 1 plus RT. Compound interest formula, your amount is your principal. Now, instead of just your rate, you have to take your rate and divide it by the number of times you're compounding. Again, think about 12% interest monthly. Well, every month you'd only do 1%, right? That's why you take your rate and divide it by N. And then how many times you're compounding the interest? Well, if you're doing it N times a year, times T years, this is how many times you're going to compound. Okay. So A is the amount after T years. P is the principal, what you start off with. R is the annual interest rate. And because R is the interest rate per year, time has to be in years. And N is the number of times compounded per year. Year. Everything's based on years. Okay. That's what makes the formula work out. All right, so a little bit of vocabulary. Annually, N is 1. That means you compound interest once a year. Semi-annually, that means you're compounding every 6 months. Quarterly, that means 4 times a year, all right, or every 3 months. Monthly, N is 12. Weekly, N would be 52. Daily, N would be 365. Now, if you go to infinity, right, then the amount is P E to the RT, where E is Euler's number, which is 2.7 something, 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 the natural base. And all right, solve. So we have $100. So that's our principal. That's how much we've invested. Our interest rate here is 2% or 0.02. How much would this be worth in 15 years? So T is 15. If we have simple interest, the amount is P times 1 plus RT. So that means they're not collecting any interest until the end of the 15 years. They only charge interest once at the end of the note, right? So we would have $100 times 1 plus 0.02 times 15. So if I'm plugging this into my calculator, I'm starting off with 15 here. I'm going to say 15 times 0.02, which gives me 0.3. Now I'm adding 1, which is 1.3. Now I multiply by 100 and I get $130. So at 2% interest, it took 15 years to get $30, which makes sense. 2% each year would be $2. So after 15 years, you get $30 of interest added. You can do that one in your head, right? $100, 2% interest, that's $2 a year. After 15 years, you get $30 in interest. So you end up with 130 bucks. Okay. Notice there's no interest on interest on interest, right? Because this isn't compound interest. This is simple interest. Now, if you're compounding it annually, what this means is during the second year, you're going to collect interest on the interest you earned from the first year. And the second year, you're going to collect interest on the interest from the first year and the interest from the second year and the interest on the interest from the first year. Okay. So we have to use our compound interest formula, 1 plus r over n to the nt. Compounded annually, that means once a year, n is 1. So we have $100, 1 plus 0.02 over 1, the 1 times 15. So I start off, work this thing on the inside out. This is 15, right? So I take 0.02, divide by 1, add 1. I got 1.02 in my calculator. Then I do to the power of 15. And now I got 1.3 something something. Now I multiply that by 100. And I get $134.59. So notice I get an extra $4.59. That's from the interest on the interest on the interest. On that 15th year, you're collecting interest on interest 15 times over again. Okay. But what if we compound monthly? All right. P1 plus R over N to the NT. Monthly means N is 12. So we got 100 bucks. 1 plus the interest rate, but we're doing it 12 times a year, so we'd only do a 1/12 of our interest rate. So we have 12 times a year times 15 years. Okay, so if I'm plugging this into my calculator, I kind of want to know what this number is ahead of time. So I'm going to look at that. 12 times 15, that's 180, okay? So now that I know what that number is, I start here, 0.02, divide by 12. Now add 1. Now to the power of 180. So I got all of that now. Now times 100. And I get $134.95. So I got an extra, what? 36 cents, something like that. 60, yeah, extra 36 cents. Because they're compounding it 12 times a year instead of just every year. Now, if we compound weekly, that means N is 52. So again, compound interest, 1 plus R over N, the NT. We got 100 bucks. We have 2%, but we're doing it 52 times a year. So every week, it's only a 52nd of the interest rate. And we do this 52 times a year times 15 years. So the first thing I need to know is what this number is if I'm going to use my simple little calculator here. 52 times 15, that's 780. That's how many times we're going to compound interest over the 15 years. So I take my 0.02, I divide by 52, and I get 0.00038, whatever. Now add 1. I got 1 point something. It's a number just barely bigger than 1, but I'm going to raise that. Even though this is something just barely bigger than 1, I'm going to raise it to the 780th power. And I end up with a 1.3 something. Now I multiply by 100. And I get $134.98. So I got an extra 3 cents by going from monthly to weekly. Compounded continuously, and you see continuously, that's an altogether different formula. This is amount equals PE to the RT. So we got 100 bucks. The interest rate is 0.02. The time is 15 years. Okay. So to do this one, let's see, how do we do this? there's an e to the x button, okay, on your calculator. You have to type in this first, and then you hit the e to the button, right? If you hit the e to the button first, if you hit e to the x, your calculator has 0 in it when you just open it up fresh. If you hit e to the x, it tells you 1, because anything to the 0 power is 1. All right, so we need to know what this number is here first. 0.02 times 15. This is 0.3. All right, so I have 0.3. Now I hit e to the x, and that tells me 1 point something something. Now I multiply by 100, and I get $134.99. So I got an extra penny. And that's the most interest you're going to get, is if they collect interest, compound interest continuously, every billionth of a second. All right. So from simple interest to compounding continuously, the most you're going to get is the extra $4.99 in this particular example. Okay. So y'all need to know which one of the formulas to use. There's 3 of them: simple interest, compounding n times a year, or compounding continuously. So you look for simple, compounded, and compounded continuously, right? That's how you know which formula to use. So let's look at another one. All right, we have $800. That's our principal. 5 years, that's our time. Our interest rate is 2.5%, which would be 0.025 as a decimal. Simple interest, the amount is the principal times 1 plus RT. Principal is $800. R is 0.025, and then the time is 5 years. So I start off with this 0.025 times 5. Now add the 1. Now multiply by 800. And we get $900. Okay. So an extra $100. Compounded annually, amount is P times 1 plus R over N to the NT. So our principal is 800. Our rate is 0.025. We're compounding once a year. So the number of times is once times the 5 years. So if I'm going to figure this out on my calculator, I start here. 0.0125, divide by 1, add 1, raise it to the 5th power, and now multiply by 800. And we get $905.13. So we got an extra $5. If we're compounding monthly, I forgot to put up here, N is 1 for annually. Monthly, N is 12. So we have the same formula. We have our 800, 1 plus our interest rate, but now we have to divide it by 12. We have 12 times 5. Okay, this is 60. I need to know that ahead of time. So I take my 0.025, divide by 12, add 1, raise this to the power of 60. Now multiply by 800. And I get $906.40. Got an extra $1 or so, right? We're doing this weekly, N is 52. So we have $800, 1 plus the interest rate divided by 52, and then 52 times the 5 years. So I need to know what that is. 52 times 5 is 260. So now that I know that, I'll start here. 0.025 divide by 52, add 1, raised to the power of 260, and now multiply by 800. And I get 906 and 49 cents, an extra 9 cents. Compounded hourly. How many hours are in a year? Right? 1 year is 365 days. And then we have 24 hours per day. So 365 times 24. This is 8,760 hours. So compounded hourly in is 8,760. Okay. So using our formula, we got 800 bucks, 1 plus 0.025 over 8,760 to the 8,760 times 5. So I need to know what that number is first. And it is 43,800. That's what that number is. So 0.025 divided by 8,760, add 1, raise this to the power of 43,800. Now multiply by 800, and I get $906.52. 52 cents. So we got an extra 3 cents by going from weekly to hourly. We're compounding continuously. Boom, we have to use our continuous compounding of interest, the one with the e to the RT. So we got 800 bucks, e to the 0.025 times 5 years. So for my calculator here, I go 0.025 times 5, then e to the x times 800. I got $906.52. Exact same I got before. It wasn't even enough to make a cent difference going from hourly to continuously. So let's look at some exponential decay. Well, no, it's decay. This is growth. So the growth of a bacteria colony can be modeled by the function below, where n is the number of bacteria in thousands, and the t is the time in minutes. All right. So the initial population of the bacteria, if time is 0, then n is 25 times e to the k times 0. This is 25 e to the 0. Anything to the 0 power is 1. So it's 25, but n is in thousands. All right. You can always see with an exponential function, if you put 0 here, this is just 1. So it's really easy to see the initial population is 25,000. Okay. That's the way exponential functions work. They're really nice. When you get into trigonometry, you got all these trig functions. But if you use complex numbers, all your sines and cosines turn into e to the I theta. I'd rather work with e to the I theta than cosine theta plus I sine theta. Right? These are easy to manipulate. These kind of suck. Okay, so that's why complex numbers are important and exponentials, because then you can get out of doing trig. So if the growth rate is 1% per minute, so R is 0.01, again, when you're doing finances, everything is annually, right? And time is in years. Here, this is per minute. Well, T is in time per minute for this formula. How many bacteria would you have after 2 hours? Well, 2 hours, that would be 120 minutes, right? You have to convert it to the right units here. So in here, n is a function of time. So if we plug in 120, we have 25 times E K times 120 growth rate. Oh, I said R equals 0.1. It's K, right? Why do they use K instead of R? They usually reserve R for annual interest rate. If they're doing a different time base, they'll use the letter K instead. Okay. So we need to replace K with 0.01 times 100, what, 120? All right, so use K instead of R when not using years for time. Okay. So it's just a different letter. It represents the same thing. It's your rate. Okay. It's just in finances, they use R, and anything else that's not annual. If it's not an annual interest rate, then they use the letter K. Okay. So we plug this into our calculator. We start up here in the top, we take 0.01 times 120, which is 1.2, and then we do the e to the x, and now we multiply that by 25, and we get 83. So this would be 83,000. So after 120 minutes, starting off with 25 bacteria, after 120 minutes, we suddenly have 83,000 bacteria. All right, suppose 7,000 bucks is invested. That's our principal. Annual interest rate of 5%. So R is 0.05. Compounded daily. So N is 365. Find the total amount in the account after 12 years. So that's our time. So since this is compounded interest, we use A equals P 1 plus R over N to the NT. So we got 7,000 bucks. Interest rate is 0.05. We're compounding 365 times a year. And we're doing this for 12 years. Again, to figure this out, I need to know what this number is ahead of time. 365 times 12. That number is 4,380. Now that I know what that number is, I start here, 0.05, divide by 365, add 1 to that. And now I hit to the power of 4,380. And now I multiply that by 7,000. And I get $12,754.31. Got to keep my dollar sign there. All right, I have 10,000 invested. That's my principal. Interest rate of 4.25%. So R would be 4.25%, which would be 0.0425. Compounded continuously. I see that continuously. That means I use this formula. Find the total in the amount in the account after 35 years. So T is 35. So we got 10 grand. E to the 0.0425, dang it, 25 times 35 years. So I start here, 0.0425 times 35 equals, and now E to the, so I did that, and now I multiply by 10,000 times 10,000. The hell? I did something wrong. Hold on. 0.0425 times 35 e to the times 10,000. There we go. We end up with $44,260.17. Which isn't bad. I mean, 10,000 bucks and now you got 44,000. It's only 4.25% interest rate, but it is 35 years. That's a long time, right? 35 years to quadruple your money. All right, an investment property in 2016 was worth 375,000 bucks. If it decreased in value at a rate of 3.5% a year, compounded annually means n is 1. What will it be worth in 2030? So 2016 is time 0. 2030 would mean, how many years later is that? 14 years? That's 14 years later, right? Okay. So at time 0, it was worth this much. So this is our principal, basically, 375,000 bucks. It decreases. So our interest rate here is negative. It's negative 0.035. Okay. So since we're doing compound interest, we need to use our compound interest formula. All right, so we start off with a house or property worth 375,000 bucks. And let's see, our rate here is a negative 0.035 over 1. And 1 times 14 years. Okay, so this is not too bad. This is just negative 0.035. So we just do 1 minus 0.035. Notice that's a number less than 1 because we started off with 1 and subtracted some from it. So we got something a little less than 1, and now we're going to raise it to the 14th power. Now I got something a lot less than 1. It's like 0.6. This was like 0.9 something. But when you raise it to the 14th power, now I only have 0.6. Now we multiply that by 375,000 and we get 227,726.54. So we lost about 150,000 bucks. All right, at 3.5%. All right, so let's do exam. What is this, 24? Okay, let's see. We still got more examples to do here, but page 178. So here's your number 1. Here's your number 2. Okay, so remember, continuously, you have to use this one, right? And semi-annually, that means twice a year. All right, so you have to use this one. Okay, those are your hints. And that's it for today, folks. I'll see y'all Wednesday. It's done. No problem, Brian. Stop. Got it, Jason? All right, cool. See you next time.